What is dark matter? Or dark energy? Are they truly dark? Actually, it might be more accurate to call them invisible. Around the 5th century BC, Leucippus, I believe, put forth one of the most enduring scientific ideas ever. He said that everything we see is made up of tiny, indivisible particles called atoms. If you think about it, for that time, 2,500 years ago, it was an excellent theory. At the very least, it was much better than the prevailing idea that everything was composed of elements like air, water, earth, and fire. However, there was one point where Leucippus was mistaken. Atoms are, in fact, divisible. Oh, how far we've come. Thousands of years after Leucippus, we now know that his idea of the atom only accounts for a small fraction of what the universe is made of. There's something else in the vast remainder. If I were to ask you, what is the universe made of? What would you say? Space and matter, right? Meaning planets, stars, black holes, asteroids, comets. We refer to these as normal matter and energy. But then there's also dark matter and dark energy. Did you know that these celestial bodies, gas and dust clouds, account for only 5% of the universe? Perhaps the truly abnormal ones are what we call normal, and what we call dark are actually the normal ones, because they make up the remaining 95%. In short, the universe is essentially composed of two great forces. One is dark matter, which holds galaxies together, and the other is dark energy, which continuously expands the universe. And then there's what we can observe. As science strives to unravel the universe's secrets, each new discovery makes things more complex, more inexplicable. In this video, we'll discuss a reality that complicates matters even further: dark matter and dark energy. Both are concepts still very much at their beginning. We could even say we know nothing about dark energy in particular, yet we are quite certain of their existence. Since we can't see them or directly observe them, how do we know they exist? Where did these concepts come from? Let's take a look together. Do you know the proportion of heavy elements in the universe that are directly important for our lives? It's only 0.03%. The rest is made up of 0.3% neutrinos, 0.5% stars, and 4% free hydrogen and helium found between galaxies. The remaining 25% is dark matter, and 70% is dark energy. Incredible, isn't it? We need the concept of dark matter. In fact, we are certain of its existence because mathematical equations and some indirectly observed effects clearly demonstrate its presence. In astrophysics, dark matter does not interact with electromagnetic waves, such as radio waves, visible light, or X-rays. Its existence can only be determined by its gravitational effect on other matter. For instance, regions with high amounts of dark matter bend the light passing by them. This way, we understand that something interacting gravitationally, a dark substance, exists. In 1932, a Dutch astronomer named Jan Oort studied the motion of stars in the outer regions of the Milky Way and noticed something. Our galaxy resembles a disk. Jan measured the distances of stars above and below this disk. He calculated how much mass the Milky Way would need for these stars to remain at those heights and depths. But he observed something very interesting. His calculations showed that the total mass required was 3 times greater than that of the visible matter. Later, in 1933, the American astronomer Fritz Zwicky analyzed the Coma galaxy cluster, which contains over 1,000 galaxies. When he calculated the gravitational force needed to hold these galaxies together, he was also very surprised, because his calculations required a much greater mass. With the existing visible mass, the galaxies should have been rapidly moving away from each other. Zwicky's claim wasn't taken seriously for 40 years. Let me explain how Zwicky made these calculations. As you know, the Moon orbits the Earth at a specific speed. If it spun faster, it would fly out of orbit. If it spun slower, it would fall onto Earth. Similarly, if Earth's mass were greater, the Moon's orbital speed would be higher. In short, by knowing the Moon's orbital speed, we can calculate the Earth's mass. And by knowing Earth's orbital motion, we can measure the Sun's mass. If we apply this principle to the orbits of stars around galaxies, we can calculate how much gravitational pull there should be, and consequently, how much matter should be in our galaxy. If there isn't enough matter, then there must be a substance we can't see or measure directly, but whose existence we can infer indirectly: dark matter. The work of these two scientists was very valuable, but it wasn't taken seriously enough. The existence of dark matter would finally be proven in the 1970s by Vera Rubin and her colleagues from the Carnegie Institution of Washington. This team discovered that they expected the speed of objects to decrease as they moved further from the galactic center, just as in our solar system, where planets further away orbit at a slower speed. Instead, they observed that the speeds of objects in the galaxy were relatively uniform. Their rotational speeds did not decrease as they moved away from the center. Then they looked at other galaxies, and the result was the same. According to this observation, if all the matter they observed was all there was, these stars in the galaxies should have been regularly flung out of the galaxy. But they weren't. There was only one explanation. There had to be dark matter holding all these objects within the galaxy. Dark matter is actually a special form of matter. The reason we call it dark is because it doesn't emit or reflect light. Therefore, dark matter is transparent and completely invisible to us. Scientists believe that dark matter formed during the Big Bang, just like visible matter, and had a significant impact on the early universe. Through complex measurements, they can calculate how much space dark matter occupies in the universe and how it's distributed. They cannot say whether dark matter is composed of known particle types, like quarks, leptons, or bosons, or if it's made of a different unknown type of matter. Consider that over 80% of the matter in the universe is dark matter, and many projects are underway to prove its existence. But to this day, we haven't observed a single particle of it. Our definitive knowledge about what dark matter is not is greater than our knowledge of what it is. Dark matter is not antimatter because antimatter interacts with normal matter and releases energy, whereas dark matter does not release energy. So, could dark matter be a black hole? That's not possible either, because even if we can't observe black holes directly, we can observe the radiation produced by the matter that gathers in their event horizons. As you know, a photo of a black hole was even captured in 2019. Could dark matter be neutrinos? Neutrinos are tiny, fundamental particles that move almost at the speed of light. They can pass through known matter rapidly. It's a possibility, but recent discoveries show that dark matter cannot be neutrinos either, because the total mass of neutrinos is not enough to explain the effect of dark matter. So, if dark matter isn't this or that or the other thing, then what good is it? According to scientists, dark matter is a kind of network that connects the 2 trillion galaxies that make up the universe. This network made of dark matter carries the necessary materials for galaxies, much like roads connecting houses and workplaces in a city. If these roads didn't exist, we couldn't build houses. If there were no dark matter, galaxies wouldn't have formed. Dark matter isn't just that. It might also be a kind of mortar used in the construction of buildings. This is because in the early universe, it provided the necessary mass for the gas and dust clouds filling the universe to collapse and form stars. Additionally, according to calculations, the time required for normal matter to collapse and form galaxies, stars, and planets since the beginning of the universe has not yet passed. It is the gravitational pull of this invisible dark matter that accelerated this process. Even though there are many uncertainties about dark matter, one thing is certain. If dark matter didn't exist, we wouldn't be here today. It is one of the fundamental components of life. Galaxies, stars, and planets exist in the universe because of dark matter. We've somewhat understood what dark matter is. Now, let's move on to dark energy. But I must warn you beforehand. Regarding the substance we believe to be most abundant in the universe, we know the least about it. In fact, we know nothing at all. We only believe it exists. The universe is constantly expanding. We've discussed this before. But when it comes to finding an answer to the question of why it's expanding, this quest leads us to dark energy. It does lead us there. But when we ask what dark energy is, we don't get an answer. Scientists can only tell us how much space this mysterious energy, which expands the universe, occupies in the universe, and nothing else. Everything we know to date, ourselves, planets, stars, galaxies, quasars, are within the observable universe. However, as I mentioned at the beginning of the video, what we know constitutes only 5% of the entire universe. Dark energy, on the other hand, makes up 70%. So how do we know such an energy exists? In the 1900s, Edwin Hubble observed that the light emitted by galaxies was redshifting. He discovered that fainter galaxies further away showed more redshift, while closer galaxies showed less. This meant that objects in the universe were constantly moving away from each other. In other words, the universe was continuously expanding. A second piece of evidence for the universe's expansion is the cosmic microwave background radiation. Now, we discovered that the universe is expanding. That wasn't enough. On top of that, we discovered that this expansion is actually accelerating. So, what is filling the new empty spaces created by this expanding universe? Dark energy.
Along with ordinary matter, dark matter tends to stop or slow down the expansion of the universe due to gravity. Dark energy, however, causes space itself to expand. According to scientists, as time passes, the gravitational pull of normal matter and dark matter weakens, while the repulsive force of dark energy remains constant. As a result, the expansion accelerates. Dark energy acts as a repulsive force on galaxies. Its existence has been established in this way. The first thing we know about dark energy is that we cannot observe it because it doesn't emit any radiation. Secondly, as its name suggests, it is a type of energy. We can only know of its existence through its effects. There's a big difference between dark matter and dark energy. Dark matter might be clumps of objects or simple particles similar to what we know, clustered in certain regions. In contrast, dark energy is homogeneously distributed everywhere. It's even thought to be a property of space itself. I suppose some of the biggest mysteries about the universe are dark matter and dark energy. There's an unknown reality in unknown places, an unknown reality that is currently passing through all of us. It's invisible, but it exists. Let's see if one day we can unravel its secrets. Until next time, stay curious.